here's how to make an adaptive milling toolpath. So what we'll do is create an operation that is in the mill contour type. We'll go to adaptive milling, and we're going to go ahead and select our 3/4 end mill. I'm going to go ahead real quick and just say OK here and drag this up to the top of my program for verification purposes. Open up my toolpath, and what we're going to do is rough out the top of this part down to this level. If I turn on my material really quickly, you'll see we're going to cut all of this here away down to this flat level face here. In the adaptive milling toolpath, an adaptive style of cutting motion is referred to as HEM, or high efficiency milling. This is going to be very similar to a dynamic toolpath in a software called Mastercam. So what we'll do is just first look at our geometry. Like a lot of other toolpaths, you have your side stock and your floor stock, so walls and floors. We can condense that into one, or we can leave it for both. The beautiful thing about high efficiency milling is you can finish floors a lot of times with the cutter while roughing material away. Since the tool is contacted on that floor the whole time, it actually tends to leave like a very nice finish. So what I'm going to do is say I want to leave 30 thousandths on my walls, so it'll cut up to this cylinder or this boss here, and it's going to leave 30 on there, and I'm going to leave 0 on my floor. So I want to finish this flat face as I cut inward. Here you can see your check geometry, which would be my fixture. You can leave stock to that check. We could add a trim boundary if we needed to, but for right now, we do not. We do not need any kind of containment. We're just going to leave this wide open. We have our tool. We're going to do a constant step over of 30 thousandths, just for this demonstration. That'll be a good, easy number. And then here for your common depth per cut, we have a max distance of 95% of the flute. With high efficiency milling, it's generally best to engage as much of the flute as possible, especially in hard metal. It'll definitely increase your tool life. And just best practice is to kind of bury that tool and use as much of the flute as possible when stepping over. So we'll go ahead and stay a little bit off of the max flute length that we have and stick with the 95%. Our tool axis will be in the Z, since we're just doing a straight roughing toolpath. We can go into our cutting parameters now, and this is where most of the high-level details of the toolpath are located. In your controls, you have this option for bottom-up cutting. If you turn this to between levels, it'll allow you to scallop the part while starting the high-efficiency method at the bottom and working its way to the top. I'll give you an example for that in just a little bit, but for now, we're just going to keep that off. Low-height transfers, you don't typically have to worry about this. That's just traversing from one cut region to another. You're saying you want it to retract 10 thousandths of an inch and then move. We're going to climb cut. Our containment here we could change this to be use 3D, and if that was the case, this would look at the previous toolpaths that were created, and NX will interpret those and make this toolpath not cut air. But being the first toolpath in our program, since we moved it to the top, I'm going to leave this at none. There's nothing for it to look at. For our top of range, that's going to be where we want to start from, so we can start at the top of the part. Our range definition is going to be our depth. So here I can click this face, and it gives me this depth of 1/2 of an inch. That is honestly all you're going to use right here. So now that that is set, we can go ahead and just say OK, pop back to our program, and we'll generate this. These adaptive milling toolpaths may take a little bit longer to generate since they look at a lot of data and they really crunch a lot of numbers. So there's our toolpath. You can see it drops down off of the work, and then it's just going to, in an adaptive style, high-speed machine its way into the center. If we verify this here, it's going to start off the work. As we step through, it's going to lead in, and then just slowly high-speed machine its way into this boss. Now you'll notice that our floor here is finished and our wall has 30 thousandths on it. By doing that, you can have a very, very consistent cutting method, and it's in a very efficient toolpath. It also allows you to have very high material removal rates, typically higher than a traditional roughing toolpath. So that is the first example of how to use an adaptive milling toolpath. Now, we can go ahead and do something a little bit different here. I'm going to take this cavity mill and actually pull this up, and I'm going to change this depth really quickly to be just this top face, and we'll generate this. But what I'm going to do here is take this stock, and I'm going to go to 0 on my floor. I'm going to leave 1/2 of an inch on the side. We'll see why here in a second. So now when I go to my adaptive milling toolpath, I can open this up. I can change my in-process workpiece to be use 3D. Remember, I said whenever it's use 3D, it's going to be looking at the previous toolpaths. So now if I say OK and generate this, you'll see that it only cuts just around the boss, because this toolpath is cutting to 0, as we can see here, but it leaves 1/2 of an inch of material on the boss. So all this adaptive milling toolpath is going to do is cut around that boss. So it looks at what has been previously cut and eliminates your air time to make your program more efficient. Now, another option here is to use this bottom-up cutting. Here, we can say between cut levels, and then we'll go ahead and do a minimum cut depth of 50 thousandths, and we'll do 50 thousandths of an inch for this example on the step-up distance. So what I'm going to do is change this depth right here to be this floor right here, 1 1/8 inches down. So by having that turned on, when I generate this toolpath, you're going to see that it will high speed around the outside of the part, but then at the same time, it's going to come in and scallop out some of these features that are more 3D. So looking at this with just the toolpath lines, you can see there's a flat cutting motion here at this level right here that'll take all the material off around the outside. Then it's going to jump up and scallop out this chamfer that we have around the top of the part every 50 thousandths of an inch. Since I don't have any containment boundaries, it also decided to jump down into this middle section in ramp, and then you can see it has a step up 50 thousandths up to scallop that chamfer. So when we replay this now, it's going to machine around the outside, step up, and scallop. It's going to high-speed machine in this pocket. And then at the end of this depth here, it's going to have one more step up for a scallop. And there it was right there. You can see that scallop. So what it does is it starts at the bottom depth and then works its way upward to the part and scallops all these features as it goes. So by doing this, you can get a much more near net shape of part in roughing while using the high efficiency methodology.